Okay, so as we have been discussing that the carriers of heat in different materials are electrons, phonons, photons and atoms. So you see that in solid material the carriers will be phonons, in conductors it will be electrons, semiconductors will be phonons, while by radiation, if the heat transfer is taking place by radiation, it will be photons. So we see that if the length in which heat is being transmitted, let us say we're talking about the gate length of a FET. If it is of the order of mean free path of the electron or of the order of the de Broglie wavelength of the electron, then what will happen? So this is what we are going to try. We'll try to understand this. So we have also seen that heat transfer takes place by conduction, convection and radiation. Now let's try to understand that the energy associated when heat is available in a system is given by kT, where Kb is the Boltzmann's constant. So we see that the amount of energy carried by a single heat carrier in a system is given by E, which will be always quantized because Kb will be a constant number depending upon the material. So at 300 degree Kelvin, this much amount of energy will be carried by a single heat carrier in a system. So let us see what we mean by single heat carrier. So we know that in ideal gas law, PV is equal to nRT, where N is given by the total number of gas molecules divided by the Avogadro's number. Okay, so we see that so energy of each molecule in a gas will be given by PV upon capital N. So so let's just rearrange this equation, putting N upon Na here and finding out PV upon N. So N is the number of total number of gas molecules that are there. So the total energy divided by the total number of gas molecules will give us the average energy associated with a single particle. So it comes out to be RT upon Na, and R upon Na is given by the Boltzmann constant, and therefore it will be kT, and therefore we can say that kT is actually the energy associated by a single heat carrier in a system. Okay, so we have been studying about heat conduction, and we will be discussing conduction and radiation in detail. So the rate of heat conduction is given by Kc A delta T upon delta X. So this relation, what is the origin of this relation? This we can understand over here. Let us say that if as heat is transferring from one side of this material to the other, then this rate of heat transfer will actually be more if the area is larger, and it will be lesser if the thickness of the material is smaller, and it will be larger if the temperature difference is larger. So that is why it depends upon area, temperature difference and the thickness of the material, and therefore from here we can get this relation. And Kc actually depends upon the material, type of the material that we are using. And negative sign just means that if temperature increases from right to left, then heat transfer will take place from left to right. And this mechanism of heat transfer by phonons, we have already discussed that if one of the atoms is heated, it will oscillate with higher amplitudes, and then because the other atom ions or atoms, they are coupled with the first atom, so they also start oscillating with higher amplitudes. Thus and similarly, more and more atoms will join and they will keep on oscillating because of the heat provided to the system, and that is how the heat will be transferred from one point to the other. Okay, so we have defined thermal conductivity in the last topic. So you see Kc actually here is the thermal conductivity of the medium. So let us discuss what is thermal conductivity and how it will be affected in a nanomaterial. So you see that in thermal conductivity actually is given by this relation, where rho is the density of the carriers, C is the specific heat of the carrier, V is the average random velocity of the carriers. While a very important factor here is this factor lambda, which is the mean free path of the carriers. So mean free path is nothing but the average distance traveled before losing its extra energy due to scattering. So it means that if we have scattering mechanism, then the average distance between two scattering mechanisms will give us the mean free path, and the time that it takes to in between two scattering events will give you the relaxation time tau, average time traveling between the two scattering events. Okay, so we see that scattering will be of different types in different materials. For example, if it is gas molecules, then scattering of one gas molecule with the other. If it is a solid material, electron scatters with electron, phonon scatters with phonon, or a cross coupling will also take place. For example, electron scatters with phonons, or there might be some defects, impurities, grain boundaries, and electrons and phonons might also be getting scattered by defects, impurities, and grain boundaries. So if the scattering is more, then the thermal conductivity of the material will be lower. So you see that in a nanomaterial, so there will be electron-electron scattering, electron-phonon scattering, but there will be an additional scattering which will be the surface scattering, because the size of the material is of the order of the mean free path of the material. So it means that there will be extra scattering which will be present in a nanomaterial. So that is why we expect that the thermal conductivity will be lower in nanomaterial. Also, so this is one of the conclusions we have, that the thermal conductivity will be lower. And the other conclusion is that the thermal conduction in a nanomaterial is actually quantized. So you see that if the length of the material is in the nano regime, then only limited number of phonon energy will be available. So let us say that if you have a heat reservoir and the channel is connected to it, the heat will flow through this channel very easily if the size of the channel is in micrometer range. But as the size of the channel decreases, then the quantization of heat conduction, although heat will be always quantized, but it cannot be seen unless the size of the channel is of the order of the nanometer range. So these channels will actually allow a quantized thermal conductance. So if the structure gets smaller, only certain amount of heat can be conducted through structures. And if we want more heat to flow, we will have to increase the size of the material. So as we were discussing, that the quantum of thermal conductance, the thermal conductance will be quantized, and the quantum of thermal conductance will be given by this factor. And it is seen that it is not very easy to see quantization of conductance. It can be only observed at very low temperatures, and temperature at near the absolute zero, where the silicon nitride beam is around 100 nanometer wide. We see that if heat is added to a reservoir, heat does not escape the reservoir as fast as it is added to the reservoir, and only a quanta of heat will be traveling from the reservoir to the bulk silicon nitride. And there's a lot of research still going on in this area, and so it is not very well understood. Okay, so we can also, the next thing that we are going to discuss is the flow of heat by radiation. So everybody knows that if any object that is hot will radiate heat in the form of electromagnetic radiation. So now let us say that if a photon, so electromagnetic radiation is nothing but these photons. Similarly, a human body is at some higher temperature, so it will also radiate IR radiation. It will radiate photons and photons, and any hot object will radiate photons. So if a photon is incident on a material, then let us say we're talking about a solid crystalline material, then you know that this we have discussed in plasma when we discussed about electrons oscillating in a metal. So we know that the electrons, they are oscillating with some fundamental frequency, natural frequency they have. So if the frequency of the photons incident on the material is of the order of the frequency, natural frequency of the electron, these electrons will actually oscillate with a very large amplitude. And those waves of these oscillations are called plasma oscillations. Similarly, if the photons and phonons, so phonons are also oscillating. So we have phonon waves also in a material. So if photon and phonon waves oscillate in accordance with each other, then there will be some waves created that are called polaritons. And these waves in actual, they are usually present. Most of them, the intensity is on the surface of a material. So let us say that you have two conductors, and let us say they are metals or conductors for the time being, although this is also true for semiconductors. So you see that on the surface you will have the surface energy will be in terms of plasmons and polaritons. So let us say, so these surface waves will be, as we discussed, that plasmons and polaritons are usually present, and the intensity is the maximum at the surface. So if the distance between these two plates, which are at different temperatures, is in micrometer range, then you see that photons will be emitted from a higher temperature, and they will be emitted from both of them. So the heat transfer will take place through photons. While if this distance is decreased to nanometer range, we see that these auras which are the plasmons and polaritons, these are actually called the evanescent waves. And these auras of plasmons and polariton will actually act as heat carriers. And heat transfer rate will shoot up by several orders of magnitude when this condition is satisfied. And this kind of conduction is actually called photon tunneling. And this will only happen if the width of the gap is less than the wavelength of the photon. And that wavelength actually can also be found by Wien's displacement law, which depends upon inversely upon the temperature. So that's it about nanoscale heat transfer.